All right. So now that we have this foray into the Darshan analysis, so we're going to be using Darshan a lot in the next few sections when we talk about the different tuning parameters that are available in, say, MPI-IO, and the different, and when we talk about performance, or we talk about characteristics of I/O, right, it can be challenging, as we talked over the Q&A and throughout this day, to say that this benchmark number represents some goodness, right? That can be a little hard, but if we see quite say a small number of fairly large requests, we can infer that that's going to be performing better than the opposite, than a lot of small operations, just because of the nature of these file systems. Okay, so we're going to talk about MPI-IO, which is, I would say, not often directly targeted by applications, but it ends up being a pretty core component of the software abstraction stack for higher libraries like ParallelNetCF and HDF5. And so I will spend a pretty good bit of big chunk of time here on MPI-IO, talking about the various optimizations that the libraries provide, because those optimizations get used directly by the high-level libraries we'll talk about in a little bit. So it's as the name implies, MPI-IO is part of the MPI standard, and it's maybe a little bit weird to think about why does a message passing library have an IO chapter, but with a little bit of reflection, we can think about sending data to a file system is, well, I just said, it's like a write. Writing is like sending data. So instead of a message where you send a message to somebody, you write the data out to a file system. Reading from a file system is like receiving a message from somebody. And one of the strengths, two of the strengths of MPI are its ability to describe accesses with MPI data types. So an application has its own custom data structure. You use MPI data types to describe that information, and then you send it all off to somebody else. And that person knows what you did because you used MPI data types to construct the data, and you can pull the data apart in a way that makes sense. Well, in a similar way, you can use MPI data types to describe how the data is laid out in memory and how it lives in the file itself. Another advantage from MPI was the collective calls. And so barriers and all gatherers and all these are all optimized in the library so that users don't have to know what's the best broadcast algorithm to send data to every process. Instead, they just call MPI broadcast. Well, a similar feature happens here. Collective IO lets us know more about the access pattern and then transform that data in a way that makes sense for whatever file system is going on here. Now, I do a lot of work on one implementation of MPI-IO called Romeo, which is part of the MPitch MPI implementation. Romeo shows up in a couple of different places. We'll talk about how its role in the ecosystem. I will try to make it clear which optimizations are Romeo specific and which ones have been adopted by almost every MPI-IO implementation. There's only really now two. So I will sometimes interchange Romeo and MPI-IO, but there is a difference. Is MPI-IO would refer to general standard calls, and then Romeo would be one instance of that implementation, the library that I spent a lot of time working on. Okay. So here's a little cartoon talking about MPI-IO. We haven't seen a lot of source code in this talk, but here's a little bit. If you're familiar with the POSIX interface, you can probably do it from memory. You open a file, you get back a file descriptor, you write some data, you describe, here's a memory buffer and it's this many bytes big, write it out to this file. When you read data, you're doing the same thing. Well, MPI-IO has a little bit more contextual information for the library. I'll walk through the different pieces of that. We have, the first off, there's this communicator part. Right? So now opening a file is collective. We're telling the library all these processes that that are part of this communicator are going to be talking to this file. And that's really helpful because there's you then told the library who's involved, and then the communicator also provides not just a group of processes, but provides a context, and so that any message passing that MPI does, that the MPI IO library does, won't interfere with the application's level of communication. There's a weird thing that MPI IO does called setting a file view. The thought was that you would set this file view to describe the way data is laid out on a file, and then reuse it over and over again. In practice, the file view doesn't ever get reused, so it's just an extra step. And unfortunately, it's too late to change that, but that's what the file view is doing. And then the file view is using there's a couple of different, actually, there's a lot of different data types involved in setting a file view. There's the E type. We have counts in the data type. We're talking in terms of bytes or integers or floating points or some more complicated data type. And then the file type is saying how that data is laid out. So in this simple example, it's just contiguous chunks in the file, and there's 4 of them. And you can imagine some simple data type of vector type describing this access pattern. And then the write here happens with an MPI file write all. You can underscore all, making sure it's explicitly collective. You get a memory buffer and a count and a data type, and every process has a little bit different region of the file they're going to write to, and every process has its own local memory that they're going to send off to the file. And now we can do that collectively, and the process is all write to the file in an interleaved fashion in this example, but it could be anything. And in a nutshell, that's sort of the thumbnail sketch of MPI IO. It's not so different from message passing, although, again, file views and data types and the different collective optimizations all kind of add to the complexity here. And so people don't typically write to MPI IO directly, but we do want to use these different optimizations. So we talked about independent versus collective, and here's another depiction of it. It's worth repeating a couple more times. In independent IO, there's no way to coordinate. When processes all write to the file, it's all scattered around. It can be kind of a denial of service attack almost on the file system. There's no coordination happening here. Now, in simulation IO, we often see phases of IO and computation and IO again. For example, you want to read in the initial conditions of a data set. Do a big collective load of some data file. After you do your simulation, after you turn away at that simulation, you're going to then write out the data. Once you're done, you put the answer out to the file system. So that happens, again, collectively often. And if we do collective IO, we're telling the library a couple of things. All these things happen at the same time. All these processes are involved. The layout of the data for every process that's needed. And this is a lot of information that isn't available in the serial or independent interfaces. And the library is able to do a bit to optimize. And we'll talk about some of those optimizations a few slides from now. I talked about the POSIX interface, how it's pretty straightforward. You have this many bytes writing to a file, but scientific data is often not contiguous bytes. It could be much more elaborate. So we talk a lot about contiguous IO, which is we think big single chunks that go from byte n to byte n plus 35 or 1,000, whatever it is, all laid out in one single region. There is data like that, and so the MPI IO library needs to make sure that it can write that efficiently. But in scientific data, you can quite easily describe non-contiguous regions. For example, the column of data out of a row major array is going to look non-contiguous on file, but logically it's one thing in the scientific code. More likely it's going to be even more elaborate than that. Particles scattered through a two-dimensional space or three-dimensional space, or some other irregular region describing a feature in a data set. Again, more information to the library gives the library a chance to optimize that and try to make things better. And we'll speak generally of I/O transformations. We're going to take the I/O, the way that the application thinks about I/O and describes the I/O to the I/O library, and then MPI/O can then write that data out in a way that is friendly to the file system, but doesn't change the layout of the data. It's not compressing data or shuffling data or appending to a log. It's writing the data the way the application thinks about the data. It's just doing so in a way that ends up being more friendly to the file system. Okay, so we can ask, how is that happening? How is that, what does it mean to do a transformation? Let me step aside just for a second. I forward referenced this slide, which came from Theta, not Polaris, but I think it's worth talking about because I think it does a great job depicting the challenge of picking the correct request size when we write to a file system. Now, obviously, down here, okay, sorry, let me start a little bit about this experiment. There are a couple thousand processes writing out data to a file system. I think this was the refer to my notes real fast. Oh yeah, this is okay. So we're writing to the grand file system. Again, just like we talked in the QA, the performance isn't huge. That's not the important part. The actual numbers are less interesting than the fact that the numbers change so much, whether you're writing a power of 2 to the file system, or whether you're writing a few bytes to the file system at a time, or a few megabytes of data to the file system at a time. And and put some error bars on here, but here this peak performance here is 1,000 is 1 megabyte at a time, which happens to be the natural block size of the Lustre file system, 1 megabyte. The way that this Lustre file system was configured, that 1 megabyte value might be different at different sites, but on ALCF Grand, it's 1 megabyte block size, and so that's the peak one. But if we wrote 1,000,000 bytes, 1,000,000 versus a power of 2 megabytes, then the performance drops dramatically because now we're not neatly aligned to the natural block size of the file system. Now, I show this graph to emphasize the importance of getting the block size right, but I also show this graph because I would hate for any application to think, oh, I need to always write in 1024 times 1024 bytes at a time. That level of detail is ridiculous for a scientist to know. Instead, the MPI/O library can keep track of that. For this file system, we've configured the default parameters on the MPI/O library to only use that size of request, and that's a helpful one example of the library isolating a very low level detail from the application. There's a certain request size that's really good. Small writes are gonna perform much more poorly than larger writes. So we use something that we borrowed from the RAID and other layers, a read modify write operation that's called data sieving in Romeo. And in data sieving, the intuition is if we do a very small write, it's going to be bad performance. So instead, we'll read a big chunk of data into memory, and then modify that data in memory and write it out to the file system. It's going to be larger, but instead of a single request, we can write out data that's soaking up multiple requests. Now, sometimes it doesn't always work. Sometimes it doesn't always work. You can imagine that maybe the ratio of extraneous data, that the data you are sieving out, is too high. And there's a point where it actually is better to write individual operations at a time. So again, there's no single value that's best for a data sieving buffer, but again, the intuition here's an optimization that the library can do on your behalf. And then with a little bit of tuning, we can dial it in and just right. All right. Well, we can use the IOR benchmark to exercise these non-contiguous accesses and learn a little bit about what is effective and not effective. So we talked about earlier in this talk, we talked about how IOR has the notion of block sizes, transfer sizes, segment counts. Well, if you use a fairly new IOR, you can describe those segments with an MPI data type. And then instead of writing out multiple segments, just write out all the requests at once. And I'll show you a couple of optimizations on how that impacts the file system. So in this toy example, we've got 4 segments. Each segment has the same block size, and then the purple process will fire those off, and the orange process will fire those off. And so if we're going to do data sieving, right? Maybe the purple process reads in these 4 blocks and throws away the 3 blocks that are being used, but then modifies that block and then writes out the disk. Here's the problem with data sieving, right? False sharing. The orange process comes through and wants to write to the same, one counts off 4 blocks in the beginning of the file, 1, 2, 3, 4, and now we have a little contention here, and we'll see that can be a problem. So if we apply the data sieving optimization, we actually get a pretty poor result. And again, this is independent operations writing to a shared file. So we're not doing the file system a ton of favors here. We're just going to see how this optimization affects performance. And there's a pretty big gap here. This was 1,000 segments writing out the file. I think it was a few hundred processes. And when we turn off data sieving using some MPIO hints, which we'll talk about in the parallel SCF section, if we turn off data sieving, we get a big jump in performance. Now, not great performance. This is from Polaris. Now we're talking about some graph from data we got from Polaris itself. In terms of absolute numbers, not great, but much better than before. So why is performance so much better when we turn off data sieving? Well, in this case, even though we ask for, so look at the data sieving column here. We at the MPI-IO layer told them, write out about 2 gigabytes of data. Instead, almost 100 times more data was both read and written as we kept pulling in blocks of data and then modifying them and writing them back out. When we turn off data sieving, we're not having an extra. There's no extra data. There's no read step. The writes turn into the 2 gigabytes of writes turn into 2 gigabytes of POSIX writes. They're not fantastic because they're kind of small writes, but there's not a lot of wasted data here. So where does that write amplification? The write amplification comes from the internal buffer not being sized appropriately for this workload or this file system, and it needs a little more adjusting. I'll show you an even better approach to that. But I want to talk a little bit more about how we can look at that access pattern. I mentioned the work that Jean Bez has been doing with Darshan data, and this is called DXT Explorer. You can ask Darshan to trace and every single operation. It's more expensive and creates a larger log, so it's an opt-in feature. But the Darshan extended tracing gives you the full operation by operation story of what happens to this file system. And it may be hard to see because at the top graph here, this is is the MPIO call. So every process here was called an MPI file write. And that single MPI file write turned into many read modified writes. I'm sorry for anybody colorblind watching this or watching this in the video later. Blue is a write, red is a read. And so we can see down here a lot of blues and reds. We also see a lot of white space because as a given process comes in, it has to lock the file, it has to request a dedicated access to the file, then do its read, then do its modify, then do its write, and then release that lock for everybody else. So there's a lot of contention going on, a lot of waiting going on. But because this is independent IO, there's not much we can do here. All we can do is transform the IO requests from small requests to larger requests, but we're not able to know anything about who else is writing to this, who else writes to this file, where are they writing, what can we do with them? There is a way to fix that though, if we use collective IO. And we take, in collective IO, there's this notion of two-phase collective buffering. And at a high level schematic, the two phases are exchange, so for a two-phase write, exchange the data among processes so that every IO aggregator has the data that is best for it to write. And then phase two is to actually do the write. Now, reading is the reverse, where the aggregators read the data in a big, say, contiguous manner, whatever makes sense for that file system, and then shuffle the data around using the fast network to get the data where it belongs. And I'm being deliberately vague about what best for the file system means, because it turns out that that is really hard to get right. Way back when we first started this little workshop, we talked about the block boundaries of file systems, the locking regions, and sharing locks, and how challenging that was to get performance. And here is why that's challenging. So in this case, we can picture a couple different ways to assign regions of a file to these MPI-IO aggregators. And I should have another figure here about the aggregation process. An IO aggregator is a process that is selected to delegate and does IO on behalf of everybody else. So let's say you have 1,000 processes that are doing IO to a file system. The MPI-IO library would pick 2 or 4 processes per node to be your aggregator, to be your IO process. And then in collective IO, all the IO routes to them. And now that might seem like an extra step, but the networks on these machines are so fast that the exchange of data happens relatively quickly relative to the IO times. And so we can do all kinds of massaging of the data here because, for example, if we just did a simple, naive, take the file from first byte to last byte and divide it among the aggregators, that would get you some parallelism, but you would probably end up with, unless you're quite lucky, some lock contention, as in this case, aggregator 1 and aggregator 2 are trying to share, trying to update or get data from the same region, same lock region of a file. Well, it's not too much more work to shift those boundaries a little bit so they match with the lock regions. And now you have all the aggregators reading the data in a natural fashion. This is what works really well on GPFS. If you dial in your buffer sizes and you align those aggregator requests so that they are on the lock boundaries, all of a sudden GPFS performance shoots up quite a bit. Unfortunately, this simple alignment isn't going to work on Lustre. With Lustre, there's a little bit more involved. You've got to be mindful of those storage servers. Each of those storage servers is responsible for the locks on a region of the file And so it actually turns out in this group cyclic distribution, you're constructing a fairly non-contiguous axis. But the point is each axis lands on one, so the axis for one aggregator lands on one Lustre server. So even though the first aggregator is writing a megabyte, and then the fourth megabyte, the 10th megabyte, and so on, those regions all end up on one server, and the cost of acquiring and revoking locks is quite limited. And again, performance is good. And that's a detail that was complicated enough to get my colleague at Northwestern, Wei-King Liao, an SC paper a while back, but is all packaged up inside the MPI-IO library, and you don't need to worry about it. So if we take the same access pattern, the same non-contiguous benchmark that we ran 2 slides ago, and we turn on collective IO, we have to change the y-axis here. But again, we see a huge jump in performance. What are the sources of that performance gain? Well, now in 2-phase, the writes, the MPI-IO level, we're asking for 2 gigabytes of writes. We're doing 2 gigabytes of writes. There's a small number of operations. They're all quite friendly to the file system. Now, I do want to draw your attention to the error bars here. I, again, don't know exactly what happened here. One of these cases was way out in terms of performance. The other 4 cases were much more what we expected. So again, challenges of benchmarking on a modern parallel file system. So now, what's the drawback here? Collective IO implies temporal coherent, that everyone's in the same time when they do the IO. If there's anybody who enters the IO late, they can't complete the collective IO. I mean, this is the same problem at the MPI layer. That was, but in IO, it still holds true. If there's a slow process comes into the collective late, the IO can be delayed. It looks like collective IO was slow, but really what was happening was the wait part of the collective IO took a while. And then once everybody was there, it all went pretty fast. All right. Again, I want to draw your attention to the GitHub page where the non-config example for IOR is there. You can play around with it. You can play around with it yourself and let me know what you find out. Oh yeah. So again, this is from so now we're up to what with the collective IO to this non-contiguous access. We're at 15 gigabytes a second for a somewhat small number of processes. Again, I'm still working on understanding how to get that number higher for shared file IO. All right. So let's go back to the 2-phase IO, this DXT Explorer timelines. I like how it depicts the aggregators working, the time aspect of kicking in. You can see a lot of what's going on. You can see a lot of what's going on here inside the MPI-IO library. So again, top chart. I had to zoom in pretty far to get that previous chart. So the 192 processes were all on separate lines. In this case, this is the full view of the DXT Explorer image. So this is one big blue rectangle, but it's actually 192 processes doing MPI-IO calls. So down in the POSIX layer, we see a couple of things. There was this exchange phase that happened, the white region of sort of a planning of data. Is this data actually a good candidate for collective IO? Should we do this? And then there are these rounds of collective IO because there was a lot of data. The 2-phase algorithm isn't going to operate on the whole file at once. Some of that memory on the node belongs to applications. And so, and I think it's 16 megabytes at a time now, although that's tunable. All the processes work on regions of the file at a time. And you can see some gaps here where processes aren't involved in IO. Those are the non-aggregating processes, and the rest of the processes are involved in the IO. And so we have 16 full round, and then a little bit of extra data at the end, where some processes have some data to do and some don't. And This pattern would look a little different if you ran it on GPSS, but it would look a little bit different, but it wouldn't be entirely different. There would still be this notion of phases of IO and rounds, and which processes are involved in the IO and which aren't. All right.